experience force when placed into electric field. Okay. And of course, electric field is space where electric force acts. Okay. Electric current is flux of electric charges. We assume that electric current flows from plus to minus, despite the fact that charges are often negatively charged electrons. Okay. In classical physics, electric current is similar to the flow of fluid. Remember, we studied fluid mechanics. Okay. Okay, so we start with electrostatics. And the law of electrostatics, as you can see, equation number 1, is similar to the law of gravity of Newton. Okay. For electrostatics, it's called Coulomb law. Okay. Coulomb law is electrostatics, and it is similar to Newton's law of gravity. The difference is that gravity can only attract, and in our part of the universe, gravity is much weaker than electrostatic force, which can repel and attract. Okay. So here is the question. Please find the force between two charges, L and T coulombs, m meters apart. Okay. So you may remember that for gravity law, the constant G was roughly 10 to the power of minus 10. Okay. And here C is 10 to the power of plus 10. So more than 10 orders of magnitude difference. So as you can see, in our universe, electromagnetism is how many times? 10 to the power of 20 times stronger than gravity force. Okay. So this code calculates the force of attraction or repulsion between the charges. I don't give you the signs, doesn't really matter. The force will still be the same. Yeah, if the charges are the same, I mean plus and plus, for example, or minus and minus, then they will repel. If one is plus and the other one is minus, they will attract. Okay. Okay. So any questions or comments at this point? Okay. So the next important notion is voltage. So voltage V between points, between 2 points, is work to move unitary charge of 1 coulomb between these 2 points. It's very significant. We will use it later on. So, and the question is about the capacitor, and the distance between the plates is D. W is work, F is the force, and Q is the charge. And work, as we know, force times the distance, just like in classical mechanics. Can you see? W is F times D. Okay. Therefore, of course, force is work divided by the distance, right? And intensity of electric field is force divided by charge, right? So force, we know, is work divided by distance, right? So therefore, the intensity of electric field is work divided by charge and divided by distance. And we remember that voltage is work divided by charge. Okay. So therefore, intensity of the electric field times the distance is equal to the voltage. Okay. So electric current, another important notion. Electric current is equal to charge over time. So charge divided by time, but that's for secondary school. For us at the university, it's derivative of charge with respect to time. Okay. So let us try to find the voltage between the plates of the capacitor, okay? So this is the code which calculates the voltage. We have the intensity of electric field, which is your student number mod 8, and the distance is your team number minus your L number divided by 10, yeah? So obviously the voltage is intensity of electric field times the distance, according to what we have just proved. Please ask questions or give comments. So this is uniform electromagnetic field between the plates of the capacitor, okay? Okay. The next question. So in this case, we calculate the force, which is equal to intensity of electric field times the charge. Yeah, we have just proved that a few minutes ago. Yeah, so that's how we calculate the force. Intensity of electromagnetic field, to be more accurate, electric field times the charge. Okay. Questions, comments, please, at any time. So now we will try to move to electric circuits. So that will be already electrodynamics. Okay. Maybe I should write it down, electrodynamics. Well, okay, so we will consider electric circuits, okay? There are many electronic elements in electric circuits. For example, resistor causes drop of voltage. It resists the current. Capacitor accumulates electric charge and then releases it. Inductor induces electromagnetic field and also resists to change of electromagnetic field, just like mass resists acceleration, okay? Diode allows electric current only in one direction using this PN junction, which we will discuss a little bit later, okay? Transistor is kind of complex diode, and transistor acts as a switch, okay? So here's Ohm's law for the circuit, basically for the one basically a unit of circuit, right? So voltage across the resistor is equal to current through the resistor times resistance. V is equal to I times R, okay? So this is Ohm's law. And we will use it to calculate the voltage, okay? This is the code, very simple, okay? Questions here? Comments, please, because we will move to resistivity if you don't have questions and comments. And resistivity is super important. So the next subtopic is resistivity, which is the resistance of 1 meter long and 1 meter squared cross-section wire. And resistance is equal to resistivity times the length of the wire divided by cross-section of the wire. And resistivity is denoted as rho, not to be confused with density, okay? It is very important because depending on the resistivity, we consider the material either a conductor or semiconductor or something which does not conduct electricity at all, isolator, okay? It will be very, very important for later on, but now let us calculate resistance given the resistivity, okay? Just length times the resistivity divided by cross-sectional area. Questions, please. Comments, please. Okay. Now, electric current follows the path of the least resistance. And direct current is current from plus to minus in one direction. Okay? So here is the question about the compound resistance in parallel and in series. If it is in the series, then we just add up all resistors, right? All resistances, R1 plus R2 plus R3. And for the series circuit, the current is the same, and the total voltage is the sum of the drops of voltages through the resistors, okay? Whereas for the parallel circuit, the voltage is the same, right? And the sum of the currents through all resistors will be the total current, okay? Please ask questions or give comments, or both. So I expect you to calculate compound resistance of resistors in the series and in parallel, okay? Okay, so here is Kirchhoff's law, which says that for electric circuit with electromotive force of E with internal resistance R and active resistance R big, electromotive force is equal to I times R big plus R small. It is, as you can see, very similar to Ohm's law, but just a little bit more complicated. Here, I is the current in the circuit, okay? And, okay, question or comment? Just a moment. Look, electrodynamics is applied in many spheres. Motherboard, of course, is one of the examples because this is a circuit, complex circuit, and of course, electrodynamics is indeed applied there. But I will think about your question. Interesting question. Maybe I can answer it better, okay? Okay, so I hope you can see what I see. I would like to share the file. Kirchhoff's law. Okay, I hope you can see that. So it's Kirchhoff's law. Okay. Let me try to stop sharing this, and I will share Kirchhoff's law. Can you see that, Kirchhoff's law?
Yes, sir.
Can you see like E, R big, R small, and then Kirchhoff's law? Can you see that? So the waste in this circuit, just like in any circuit, is current times active resistance squared, okay? I hope you can remember that, but I will try to give you this picture. It's everywhere in every book, in every website, but I just would like you to know that the waste in the circuit is current times the active resistance squared. It's basically power. Power is voltage times current, right? And but using Ohm's law, we can rewrite voltage as basically voltage through the resistance. Yeah. So in this case, we have waste equal to I times R squared. Yeah. Let me think. I need to think about that. Okay. Anyway, the waste is current times the resistance squared. Okay. So let me stop sharing this and go back to the file of the Kirchhoff's law and the question, which asks you show that the maximum loss in the circuit with internal resistance R small and external resistance R big is when R big is equal to R small, okay? So R big is something we plug in. For example, your laptop, your air conditioner, your lamp, your fridge. That's active resistance. We can vary that. We can on and off. We can make it bigger or smaller, right? And as you can see, the waste will be 0 if current is 0, or if the active resistance R big is 0, right? So if we calculate the derivative from the waste, we will definitely get maximum, yeah, because we have already proved that minimum will be for R big equals 0 or for current I equals 0, right? So we express current I through the Kirchhoff's law, which is E over R big plus R small, yeah? And then we plug I into the waste expression, right? So we get R I squared is equal to R E squared divided by R big plus R small squared, okay? And now we take the derivative with respect to R big, yeah? And that's what we've got. So we use the simple rule of derivative of the quotient, right? So indeed, the derivative is equal to 0 if R big is equal to R small, right? Because R big cannot be 0, R small cannot be 0, so denominator is positive. E squared cannot be 0, so only R big minus R small must be 0. So therefore, indeed, the maximum waste or loss for R big is equal to R small, yeah? And for some people, it's very confusing. They may say, oh, how can that be? Why not half of R or like 2R or something like that? No. So the internal resistance of the electromotive force source is a fixed number. We cannot change that, right? So for example, your battery has a fixed internal resistance of R small. But we can vary R big. We can plug and unplug our fridge, our vacuum cleaner, our air conditioner, what else we can on in our house. You know, as you can see, we can vary the active resistance, and maximum losses are for active resistance equal to the internal resistance of the source of electromotive force, okay? So therefore, make sure that your active resistance is not equal to the internal resistance of your source of electricity, okay? Any questions, any comments, please? Okay. So now we move to alternating current if you don't have questions. So alternating current basically goes back and forth. So plus and minus switch, they swap. So the current goes one direction, then the other direction. And it happens in LC circuit, for example, which is basically used in all communication devices, like your mobile phone, computers, the internet, all of them use this kind of basic device to transmit and to receive electromagnetic signal, yeah? It is very important to be aware of Faraday's law, which shows how the inductor works and how changing electric field causes changing magnetic field, and changing magnetic field causes changing electric field, yeah? So mechanical oscillator and electromagnetic oscillator are very similar, and we will consider electromagnetic oscillator LC circuit, okay? So for LC circuit, we only have capacitor and inductor in our circuit, okay? Just like the spring and mass or pendulum, it is a harmonic oscillator which has the same differential equation number 2. Can you see? So for pendulum and harmonic oscillator in mechanics, we had y coordinate, unknown. And here we have charge unknown. So Q is the charge. So the second derivative of charge plus charge divided by capacitance times inductance is equal to 0. And this is the same differential equation. We solve it, and we find that the natural frequency, just like in the case of pendulum or harmonic oscillator in mechanics, it's the square root of whatever is the factor of Q, right? 1 over LC, so 1 over square root of LC. Remember, for the pendulum, it was square root of K over M, of G over M, and for harmonic oscillator on the spring, it was square root of K over M. Yeah, in this case, it's square root L times C, where L is inductance and C is capacitance. Okay. So, and we calculate the period. Period is 2 pi times the omega, frequency omega. Yeah, just like in harmonic oscillator or mechanical harmonic oscillator or pendulum, it's basically the same. Mathematically, it's the same. Just the numbers are a little bit different, and the physical meaning is different. Yeah. So questions or comments? So this is probably the most important in electronics and in telecommunications, like the basics of telecommunications, LC circuit, harmonic oscillator. It will oscillate forever. And we neglect all the resistance which takes place in this kind of circuit. Okay. Please ask questions, give comments, because now we will consider a little bit more complex circuit, which is more realistic. And this circuit is RLC circuit, okay? So in addition to capacitor and inductor, it also includes the resistor R, okay? So here is the question. The question is, we need to find electrical current I in this RLC circuit. As you can see, the equation is also exactly the same as for forced oscillation in mechanics. Yeah, and solution will be exactly the same, just like in mechanics, but the meaning will be different. Okay, so what I would like you to do, I would like you to open. Can you open this link, please? I will try to send it to you through chat. Could you please open this link? I'm sending it to you through chat. Can you? Can you open? Hello? Can you open the link? Hello? Can you open the link? Yeah. So
Yes,
as you
sir.
can see, they give you, yeah. Unfortunately, I cannot see the link myself. Maybe I will try. Maybe I can see it somehow. No, I cannot see it. I cannot open it. Can you open it? Oh yeah, I opened it. Okay, nice. Yeah, me too. Okay, great. So it solves many problems, but I want you to look at slide number 1, right? As you can see, it's LRC circuit, right? Can you see capacitor, inductor, resistor, and the source of electromotive force? Yeah. So here is the solution. Yeah. Can you see the solution is epsilon divided by R, right? And basically what we need to find EM, and then we will have our solution, right? So IM, yeah? So IM is equal to epsilon M divided by Z. And Z, if you scroll down to the slide number slide number 8, slide number 8, right? As you can see, Z is the total impedance, total kind of compound resistance. It's expressed through the active resistance and passive resistance of inductor and capacitor. And passive resistance of inductor and capacitor is here, up here, right? Omega L, omega, L, and passive resistance of capacitor is 1 over omega C. You know all of these things, so you have the answer to your, you have the solution to your equation, right? And I want to show you the differential equation. I hope they can show it. Just a moment. Where is the differential equation? Slide number. Oh, there we go. So slide number 6. As you can see, the differential equation with respect to I. And I, as we know, is the derivative of charge Q, right? So if we plug charge Q instead of I, it will be the second derivative with respect to charge Q. Yeah? I think they should have written it properly. But anyway, by the way, this slide solves many problems. It solves not only this problem, but it solves the problem of transferring electricity, and also the problem of transformer. And we will get back to this slide hopefully a little bit later, yeah? But at this stage, I would like you to be able to show me how you solve the LRC circuit with external electromotive force, yeah? How you solve this differential equation and how you find the current, okay? Questions? Okay. Please, this is very complex stuff. This is very complex. And I'm sure you have many questions, yeah? Okay, so if you don't have questions, if you don't have comments, let me check. No questions, no comments, okay. So then we will probably move to maybe one of the most important topics in electromagnetism, semiconductors, electrical resistivity, and electrical conductivity, and ultimately conductor and semiconductor, okay? So semiconductor is something between insulator and the conductor, yeah? So we can use them for diodes, for transistors, and p-type semiconductor has excessive positive charges, and n-type semiconductor has excessive negative charges. And we use it for transistor and for diode, yeah? So p-n junction is basically diode. It allows current from P to N, right? If positive charge moves from P to N, it is allowed to move, but the opposite direction of current is impossible. So the positive charge cannot go through N to P. So from left to right, it can go. From right to left, it cannot go. So it's basically a diode, p-n junction, right? But what we need not only the diode, we need something more complex than diode. We need transistor, we need a switch, okay? We need a switch which uses p-n junction to basically open and close the gate for the large current, okay? And I would like us to deal with the gates not and or using transistor, okay? So let me try to share this slide with you. So a NOT gate, Let me try to open NOT gate. Okay, here is the NOT gate. Let me try to share it. Okay, NOT gate. Sharing the screen. NOT gate, okay? Can you see that? I hope you can see that. There is a resistor R, there is a transistor. So input of transistor, small potential, as you can see, small minus and then small plus, and then output. Output will give us a big plus or big minus, right? So as you can see on the bottom, big minus, for example, minus 10 volts, and on the top, big plus, for example, plus 10 volts. And then if we input, let's say, negative 1 volt, very small potential, the transistor will be closed, so its resistance will be huge. So therefore, resistor R will have much smaller resistance, and we know that the current follows the path of the least resistance. So the big plus will flow through R resistor to the output. So the output will be big plus. If input is small minus, the output is big plus. Do you understand? I hope you understand. Now, if the input is small plus, then the transistor will be opened. Its resistance will be almost zero. And because the current will follow the path of the least resistance, because the resistor R in this case has much bigger resistance than transistor, then very big minus will flow through the transistor to the output. And for the input of small plus, the output will be big minus. Can you see that? Do you understand how NOT gate works? That's how your computer, your mobile phone works. All electronics, all digital electronics works like this. Okay? Of course, the transistor and resistor is super small. They're like nanometers or something like that. But the idea is still the same, okay? So we're discussing NOT gate using transistor and resistor, okay? So the NOT gate requires only one input. And I hope you understand how NOT gate works. So if input is false, the output is true. And if input is true, the output is false. Do you understand that? Hello? Do you understand how NOT gate works? Hello? Well, I think you need to know how NOT gate works. I'm sure you know, because you've been studying this for at least 3 semesters. How many? More than 2 semesters, right? At the university, and you've been studying that at the secondary school for a couple of years at least, I would say, right? Okay. Okay, then if no questions and no comments, then let us consider AND gate. Let me share AND gate. Okay. Stop sharing, and I will share AND gate. Where is AND? There we go. AND gate. I hope you can see that. Yeah, okay. So this is AND gate, yeah? Can you see there are 2 inputs, input 1 and input 2. And there are 2 transistors. Can you see that? So you can think of these 2 transistors as one compound transistor, yeah? So if at least one of them is closed, then it will be closed, the whole compound transistor will be closed, yeah? So if both of them are opened, then it means that the compound transistor will be opened, yeah? So, and as you probably know how AND gate works, if the input are both false, the output is false. If at least one input is false, the output is still false. And if both inputs are true, then the output will be true. Do you understand that? So let's see how it works. So, for example, the first input is small minus, and the second input is also small minus. So both transistors are closed. Their resistance is huge. Therefore, the current will follow the path of the least resistance through the resistor R, and the output will be big minus. Do you understand? Okay. Now, if the first output is still minus and the second output is plus, it's the same thing, because the first transistor is closed anyway and compound transistor is closed. So the output will be big minus as well, right? Now, if the first transistor is opened and the second is closed, again, it's the same story. So the output will be negative. Output will be false, right? And finally, if both are pluses, then the transistors are both opened. The compound transistor is open. The resistance of the compound transistor is almost zero, and the current follows the path of the least resistance. The big plus will go through the transistors, and the output will be big plus. Do you understand? This is AND gate on the transistors and using the resistor. Questions, comments, please? Okay, finally, OR gate. Let me share it with you. So I will try to share the OR gate. There we go. So as you can see here, the transistors are in parallel. You can think of both transistors as being compound transistor, and if at least one of them is opened, then the compound transistor will be opened, okay? And as you can see, only if both inputs are negative, both transistors are closed, and their compound resistance is huge, so therefore the current following the path of the least resistance will go through the resistor R, and the output will be big minus, okay? In all the other cases, at least one transistor will be opened, and the resistance of the compound transistor will be almost zero. So therefore, big plus following the path of the least resistance will go through the compound transistor, and output will be always big plus, okay? Do you understand? OR gate based on transistors. Please ask questions, give comments. So this is probably the most important topic of physics, how the electronics is designed. Oh, sorry, I closed the file, sorry. Okay, I will share the task. Okay, any questions, any comments, please? Okay. Okay, we move to transformer, and I refer you to the PDF file because it shows the solution for the transformer problem. And here is the question: find voltage on the primary coil if the voltage of the secondary coil and number of loops in the primary coil and secondary coil is known. Excuse me. And voltage on the primary coil is equal to negative voltage on the secondary coil times the number of loops on the primary coil divided by the number of loops on the secondary coil, okay? Why minus? Because the current will be opposite, the voltage will be opposite, because they induce the opposite current, okay? And let me show you the transformer thing. Let me show you where is Just a moment. Oh, wait, so it's strange. Okay. Oh no. Huh. Okay. So let me see what I can do. Hmm. Oh no. Oh yeah. So how can I find? Hmm. Maybe I can go. Oh yeah. Okay. So transformer. There we go. Transformer. Let me share this transformer. There we go. Okay. So I hope you can see that. So you can see the primary coil V1 N1. V1 is the voltage and N1 is the number of loops, and secondary coil V2 N2. And the equation is V1 over N1 is equal to minus V2 over N2. So if you know three of those numbers, you can find the fourth of those numbers, okay? Please, questions, comments, anything. Questions or comments, please, or both. Okay, then let me share the task. So as you can see, the PDF file also solves this problem and explains once again, giving the picture of what happens and giving you the basically the solution of the problem. Yeah. As you can see, sometimes student number is called N, not always it is called S, because many years ago I called student number N. So please don't get confused. N in this case is your student number, okay? So I say S, but it's the same. N and S are the same in this case, okay? So what's next? Okay, now again, I refer you to the PDF file. Now we calculate the loss when we transmit 22 million volts versus 200 volts, okay? And we know that the losses, as you know, is equal to current times resistance squared. Can you see that? Just like we discovered when we dealt with Kirchhoff's law about half an hour ago, okay? So you can see that if the voltage is large, then the current is small according to the Ohm's law, right? And vice versa. So the bigger the current, the bigger the losses are. Therefore, people transmit voltage at millions of volts to reduce the losses, okay? And I would like you to calculate losses for 200 volts. They will be huge. And losses for 20 million volts will be very small compared to the losses for 200 volts, okay? Because of the Ohm's law and because the bigger the voltage, the smaller the current. And the bigger the current, the bigger the losses are, okay? So I also refer you to the PDF file. It also solves this problem for you and for us. Okay, so therefore, please understand that it is much better to transmit power at very high voltage and then use transformer to reduce the voltage, because at home we use voltage of about 200 volts, 220 volts, right? Whereas voltage is transmitted at millions, at least hundreds of thousands of volts, okay? Is that clear? Okay, please, questions, comments, anything? Okay. And then another important application, electric motor. So your air conditioner, your vacuum cleaner, those are all electric motors, right? Your fridge, those are all electric motors. And let's see how it works physically, right? This is the question. A circular coil of wire has the diameter of 0.02 centimeters, contains 10 loops. The current in each loop is 3 amperes, and the coil is placed in 2 Tesla external field. Determine maximum and minimum torque exerted on the coil by the field. Okay, so we can say that the torque is equal to the area times the number of loops times the current times magnetic field. And of course, minimum torque will be 0 if either no magnetic field or no current or no loops or no area. Okay, but maximum torque is going to be the area, which you know. So how do we calculate the area? The diameter is known, right? So we calculate the area as diameter squared divided by 4, right? So it's quite simple. I hope you understand that. And everything else is known. The number of loops known, current is known, magnetic field is known. Just plug it into the equation and you have the torque, okay? And of course, minimum torque will be 0, and maximum torque will be the torque which I showed you, area times number of loops times the current times magnetic field. And this is how all electric motors work. Please, questions, comments, anything? Okay. So let's do electromagnetic radiation. Okay. So basically, intensity is equal to the power divided by the area. So that's the definition of intensity. So the question says T watts lamp emits electromagnetic radiation in all directions. Assuming the lamp to be a point source, calculate the intensity of radiation at the distance 1 meter from the lamp and at the distance 2 meters from the lamp, okay? So the surface area of the sphere is 4 pi r squared, where r is the radius of the sphere, right? And then the intensity is equal to power, which is T watts, divided by the surface area. That's it. So depending on the radius, the surface area will be different, right? And because radius changes from 1 meter to 2 meters, the surface area will be changing 4 times, because 1 squared is 1, but 2 squared is 4. So the intensity will be smaller, will be 4 times smaller. The second intensity will be, yes, 4 times smaller, because the area is 4 times bigger. Okay, questions? So once again, intensity is power divided by the area. Okay. Okay. Now, another question. Waves from a source have the amplitude of 5 centimeters and intensity of T watts per meter squared. That's the intensity, right? Amplitude of the waves increased to 10 centimeters. What is the intensity now? Okay, so the intensity is equal to some constant times the amplitude squared, okay? So the way we can express this constant as current divided by amplitude squared, okay? So I is intensity, A is amplitude, and C is the constant, okay? And then we calculate the constant, and then we plug the constant in the equation, okay? So the intensity will be constant, which we calculated, times amplitude squared, okay? So we can answer question number A, and then question number B says what? The intensity of the waves increased to 100 watts per meter squared, okay? So it was T, whatever your T number, for example, I don't know, 25 or something like that, right? Then it increased to 100. So therefore, intensity increased. What is the amplitude? So amplitude will be the square root, right, of intensity divided by the constant from the equation, right? we know the intensity, we know the constant. So amplitude will be intensity divided by constant and the square root. Questions, please. Okay. So now we deal with refraction. So refraction is basically redirection of the wave, changing of the direction of the wave when the wave moves from one medium to another medium. For example, from air to glass, or from air to water, or from water to air, or from water to vacuum, or something like that. Okay. So so these are the laws of refraction. Okay. And the question asks, light of wavelength t nanometers in vacuum travels into glass, where the speed decreases from 3 to 2 times 10 to 8 meters per second, right? Determine frequency of light in vacuum. Well, we know the speed, right? We know the wave equation. Should I write it, or is it here? There we go. C, the speed of light, is equal to wavelength lambda times f frequency, right? So we have the wavelength, t nanometers, and we have the speed of light in vacuum, 3 times 10 to the power of 8 meters per second, right? So we will find the frequency, and the frequency will be the same in vacuum and in water. It's invariant. The frequency will be the same, okay? But the speed changes and the wavelength changes. The speed decreases from vacuum to glass, right? And the wavelength also decreases, right? So the wavelength in vacuum will be greater than the wavelength in the glass, because the speed in vacuum is faster than the speed in the glass. Let us see the calculation. So the frequency is always the same in both media, in vacuum and the glass, okay? So if velocity in glass is different, then the wavelength in glass will be different. So the wavelength in glass will be velocity in glass divided by the frequency, which is the same for both vacuum and glass, okay? And we have already calculated the frequency. We have divided the speed of light in vacuum by the wavelength in vacuum. So we have the frequency. Now we have the wavelength in the glass. We divided by the frequency in glass and in vacuum, it's the same. We divided it by frequency and we get the wavelength in glass. Okay. Questions, please. Comments, anything? Okay. So the next question is the same basically as the one we answered for the sound, okay? But this time it's for the light. An astronomer observes light from a distant star. A particular line in its spectrum has a wavelength of t nanometers. When measured in the laboratory, the same spectral line has the wavelength of L nanometers. Determine the change in the wavelength, okay? Well, obviously, t minus L, okay? The speed of the star, okay? So the speed of the star, same equation as for the sound. Remember, the car moved with the speed of 20 meters per second. That's what we calculated for the sound. Same thing here. Of course, the velocity will be different, right? In this case. And finally, the direction of the movement of the star. Okay, so remember, for the sound, our source of the sound moved towards the observer, but in this case, the stars move away from the observer. The star moves away from the observer, because there is a red shift in our universe. The galaxies run away from each other. So the star moves away from the observer, and we calculate in the same way as we calculated for the sound, but this time the star will move away from the observer, but everything else is basically the same way to calculate the velocity of the star. And of course, this time the difference is that the star moves away from the observer, whereas for the sound case, our car moved towards the observer. Okay? Please, questions, comments. Okay. So the next group of topics will be related to the interference, okay? We will consider the double slit experiment. And I will try to show you the picture, but before showing the picture, let's read the question. So we need to find X for the double slit experiment, and lambda is the wavelength, D is the distance, RA is the distance between the slits, and X is the distance between the fringes. Okay, so there is a link to the textbook. Okay, but I want to show you my picture. Let me see if I can find it. There we go, double slit experiment. So let me close transformer, and double slit experiment must be opened. Okay. So let me try to show it to you. Okay. Let me share the double slit experiment. There we go. Okay. So as you can see, there are two slits and the distance between them is A. So therefore the wave moves through two slits, and as you can see on the screen, the medium fringe is the biggest, right? So many people would expect, oh, maybe the biggest fringes should be directly opposite to the slits, but no, because of the wave nature of electromagnetic waves, there is interference, and the maximum fringe is in the middle, in between the slits. Can you see that? So X is the distance between the maxima, between the neighboring fringes. Okay, so we can find X using A, lambda, and D. D is the distance from the double slits to the screen, and lambda is the wavelength, and A is the distance between the slits. Okay. Okay, so let me stop sharing this file and let me go back to the previous file. So now when we have seen the picture, we can calculate X using this equation. Lambda D is equal to AX, right? We know A, we know D, we know lambda, so we can easily calculate X from here. Distance between the fringes, which is lambda times D divided by A. Yeah. Questions? So the next problem is very similar. It's diffraction grating. It's very hard to deal with double slit experiment because the fringes are hard to identify. They are very unclear. But for diffraction grating, we have many slits, so they strengthen each other. So therefore you can see the bright spots much more clearer. Okay, so it will be the eigenvalue problem. So we will find many bright spots, and n will be the counter. It will be 0, bright spot number 0, 1, 2, 3, 4, 5, and then also bright spot number -1, -2, -3, -4, -5. So let me show you on the screen how it looks. So diffraction grating, similar but better than double slit experiment. Excuse me. Sorry for that. Okay, let me try to share the diffraction grating. Okay, I hope you can see that. As you can see, there are many waves, and I show you for maximum number 3, so bright spot number 3. So there are many ways which increase each other, which strengthen each other. So you can see very bright spot, number 3, number 2, number 1, number 0, number -1, number -2, etc., etc., etc. And it's so much better than double slit experiment because they're so much brighter, and we can calculate, for example, the wavelength lambda and other things. In my case, I calculate the number of the bright spot much easier than using the double slit experiment, which gives like very unclear fringes. Okay. Questions, please. Questions, please. Comments, please. Okay. Okay. So let's go back to the file. Okay. So as you can see, we calculate n, which is the number of the bright spot. Okay. We can calculate m using this equation. And of course, in order to make sure that n is a whole number, we must round it. We must round n, right? Because d times sine A divided by lambda will not necessarily be a whole number, okay? That's how we find the number of the bright spot using diffraction grating. Please, questions, comments, anything? Okay, so maybe one of the most important thing of electrodynamics and electromagnetism are Maxwell's equations, which describe electromagnetic field, electromagnetic induction, electric field, magnetic field. It's a very complex system of equations. I'm not going to write it here fully, but what I will do, I will write simplified equation. Can you see? C squared times d2e over dx squared is equal to d2e over dt squared, right? As you can see, it's exactly the same equation as for the guitar string. But instead of the speed of light c, it was the speed of the string movement v. But mathematically, the equation is absolutely the same, and the solution is absolutely the same. Okay? So as you can see, the solution is just the sine of x minus ct, and for the guitar string, it was the same solution, but instead of speed of light c, it was the speed of the guitar string wave v. Okay? And it's a hyperbolic type of differential equation. It's the same mathematically as for guitar string. And basically, just like we said, in classical electromagnetism, the equations are almost the same as in mechanics, in fluid mechanics, in classical solid mechanics. So the equations are basically the same. Yeah. So, and the solutions are mathematically the same. Questions, please. Comments. Okay. So, what is the color of the sun? What do you think? What do you think is the color of the sun? Okay, let me check. White. Look, white is not a color. White is the mixture of many colors. Yeah. So white is not the answer, because white is not a color. It's just basically yellow. Okay, that makes more sense. Yeah. We sometimes can see sun yellow, maybe in the middle of the day, maybe at 12 o'clock in the afternoon. The sun looks yellow. But in the evening or in the morning, the sun looks red. Yeah. So what is the real color of the sun? Okay, let me tell you the secret. Maybe you didn't know this secret, but the truth is that the sun is green. The sun is green. And if it was no atmosphere of the earth, we would see sun being green. Yeah. And let us show that this is true. So we calculate the star's brightness. Excuse me. So the color of the sun depends on its temperature. Excuse me. Any questions, any comments, please? Hello? Can you hear me? Oh, yeah. Just a moment. So, yes, exactly. Exactly. The sun, it will be green. Absolutely right. And as you can see, depending on the temperature of the star, we can calculate the color of the star. Yeah. So there is a formula. Lambda maximum is equal to known number b divided by the temperature of the star. So the higher the temperature, the greater is the frequency. Okay. So that's how you calculate the color of the star. Okay. Any questions? So then let's discuss reflection briefly, okay? So the angle of incidence is equal to the angle of reflection, and I ask you to find the mirror size and its location for a man who looks at himself in the mirror, and how can he can see his whole body with the smallest possible mirror. Let me try to show you. Plane mirror. Yeah. So this is the man. Let me try to show you. And this is the mirror. Plane mirror. Okay. So as you can see, in order for the man to see his top of his head, so the mirror must start in between his eyes and the top of his head, right? Because the angle of incidence is equal to the angle of reflection. And in order for him to see his feet, the mirror should not be lower than half of the distance between his eyes and his feet. So if you can calculate that, you will see that the length of the mirror, the minimum length of the mirror for him to see all his body is going to be half of his height, okay? Half of his total height. So half above his eyes and half below his eyes, yeah? So we don't want long mirror, we just want cheap, small mirror. What for? Why do we need big mirror? We don't need a big mirror. We can use a smaller mirror. And as long the angle of incidence is equal to the angle of reflection, we can see that we can have like pretty small mirror, excuse me, to see our whole bodies. We don't need the mirror like here in the hotel. I have the mirror from the bottom of from the floor to the ceiling. What for? It's inefficient, right? If they knew physics, they would just make the mirror, let's say, maybe half meter from the floor, and then maybe for another half meter for like very tall person, right? Maybe not half meter, but for another meter, right? For someone who is like 2 meters tall or something like that, yeah? Yeah, for someone who is very tall, okay? So therefore, we can save money by making smaller mirrors if we know physics. Okay, questions, comments, please? Okay, let's go back to the slides. I will share this. So we continue with, okay, let me show you the calculations. So indeed, the cross section of the roads, you can see convex mirrors. Let me show you what convex mirror looks like, in case if you forgot. There we go, convex mirror. Okay. Let me show you. Okay. So this is convex mirror. So it's diverging. It's diverging so that convex mirror is diverging. So you can see more objects, but they will look smaller than they are, right? So for the security person in the supermarket to see the whole supermarket, but people and objects will be smaller in the convex mirror than they really are. Yeah. So the formula for convex mirror is 1 of the distance to the object plus 1 of the distance to the image is equal to 1 over the focal distance, okay? And the focal distance is half of the radius of the convex mirror, okay? Now, magnification of the convex mirror is going to be negative distance to the image divided by distance to the object. Why negative? Because one of those distances is negative and the other one is positive. Doesn't matter which one. It depends how you choose the coordinate system, right? So that's how you calculate everything you need. Yeah, having the distance to the object and the distance to the image, you can find focal distance. You can find the radius of curvature. Knowing the focal distance and the distance to the object, you can find the distance to the image. Knowing focal distance and the distance to the image, you can find the distance to the object, etc. Okay? So let's look at the slides again. Okay. So I'm writing down the equation, right? The mirror equation once again. So DOO is distance to the object, just to be sure that it's not the same as do, right? Because if I write DO, it will look like do, and computer considers this as a command, okay? And DI is the distance to the image, and F is the focal distance of the mirror. And the focal distance of the mirror, as you probably remember, is half of the radius of curvature of the mirror. Okay. Okay. So just like we said before, magnification is minus distance to the image. Sorry, magnification is minus distance to the image divided by distance to the object. Okay. And here is the question: for convex mirror with the radius of curvature 0.02 meters, determine the location of the image and its magnification for an object of 0.0012 meters from the mirror. So we know the object distance, we know the radius of curvature, which means that we know focal distance, and therefore we can find the distance to the image from this equation and magnification factor. Yeah. So as you can see, the focal distance y minus r over 2, because that's how we choose the coordinate system. It's okay. Minus or plus, it's not really important in this case, but focal distance is minus r over 2. R is the radius of curvature. And then distance of the image from the mirror equation. And finally, magnification is minus distance to the image divided by distance to the object. Okay, questions, please. Comments, please. So we have one question, but super important question. Yeah. So today, when there is a war, it's very important to deal with spy satellites, right? So we need to calculate spy satellite lengths to know what kind of lens we need to spy after our enemies or maybe competitors or someone like that, right? So here is the question. A spy satellite camera can recognize T-centimeter objects from the altitude of n meters. N is your student number, so it's like 22 million meters, right? If diffraction was the only limitation, determine what diameter lens the camera has, okay? So there is a formula, 1.22 times lambda divided by the angle for the diameter of lens, okay? So maybe if we have time, we will prove this formula, okay? So we know the lambda and we know 1.22, but we don't know the angle, right? How do we calculate the angle? Well, because the altitude is about 22 million meters, but the object is only T centimeters, maybe like 25 centimeters, right? The object is very, very small compared to the height of the satellite, right? So if this is the case, then the angle is equal to the sine of the angle, approximately, of course, and approximately equal to the tangent of the angle, right? And we can calculate tangent and sine by dividing the object size by the height of the satellite. Height, it's altitude. Let me write as height. Altitude, height. Okay. So that's how we find the angle. We just divide. The object size by the height of the satellite. Yeah. So in this case, T times 0.01, because in centimeters divided by n, divided by the student number. Yeah, so we know angle A, we know its tangent approximately, we know its sine approximately. So we can calculate the diameter of the lens, and in this case, the diameter of the lens is going to be approximately 1 meter, which is, it's okay. The satellite can have that kind of lens. The spy satellite can have this powerful lens. Yeah. So that's it for electromagnetism. Any questions, any comments, please? Okay. Please do ask questions, do make comments. Okay. What I would like us to do, if you don't mind, I would like us to go through the task. Yeah. Because some students send me the task and the answers are not quite correct. Yeah. So I hope we can look through the task and see if we can solve it. Okay. So task. Let me try to share the task. Okay. I think this is the task. Yeah. Okay. Can you see the task 1 in physics? Hello? Hello. Yeah. Do you have any questions about the task? Because I try to answer all the questions in class. Okay. So here is introduction to physics. Just write quickly in your own words, what do you want from this physics course? Yeah. And please write a little bit about your project if you have any project. Yeah. Then units of physics, there are 7 base units, right? Mole, Kelvin, meter, second, kilogram, etc. Right? And those are the base units. And you can express unit of force using a unit of mass, kilogram, and unit of acceleration, meters per second squared. All of those are base units. Yeah. time times acceleration obviously have the units of velocity, v, because times is in seconds and acceleration is in meters per second squared. So 1 second cancels out. So t times a will be in meters per second, yeah? Now for accuracy and precision, do it for your student number, whichever your M4 is. If it is 0, then describe what is accurate and precise. So there is repeatability and correctness and etc. for the other ones. Either no repeatability, if no precise, and no correctness, if not accurate, yeah? Now, significant figures, you use, please, Atlantic rule and Pacific rule. And I hope you can answer that. Okay, so give the limits of classical mechanics in terms of velocities and in terms of the distances and the masses, yeah? Then the definitions, and yeah, just give your own words definition of those terms. Yeah. In kinematics, we calculate the derivatives to find the acceleration and the velocity if we have the equation of the distance, right? So for collisions, you have absolutely inelastic collision and absolutely elastic collision, just like for ideal gases in thermodynamics. You have absolutely elastic collision, so there is no interaction, no electromagnetic interaction. Okay. So the momentum is conserved for absolutely inelastic interaction and for absolutely elastic interaction. Yeah. Here, make sure you give the correct values, right? So your M will be L, right? Oh, I cannot change it here, yeah, because it's task. So just change the code, because sometimes the code is kind of a little bit different, right? You need to change the code to make your answers correct, yeah? So here M1 is L, M2 is T, and U1 is S, right? And U2 is K. Yeah? So for absolutely elastic collision, also please substitute correct values for U1, U2, M1, and M2. Yeah. So, oh yeah, question, comment, let me check. Yeah, because so the question is why there are so many photos of the sun on Google and the color is orange. Because those pictures have been made through our atmosphere, and our atmosphere basically scatters orange or red or yellow depending on the time of the day. Yeah, but if we could remove atmosphere, we would see the sun being green, and you can find many pictures of green sun on the internet. If you look well, you will see that the sun is actually green. Good question. Any other questions? Okay. So we do acceleration in kinematics. We prove that v squared is equal to v naught squared plus 2a times x minus x naught, just from these equations. Then dynamics, center of mass, calculating the center of mass. Yeah. So I cannot pull myself out of the mud because internal forces cannot change the location of the center of mass. Okay, another question? Yeah. Look, try to answer as many questions as you can. And as you can see, not all questions are for your student number, right? If it is a general question without the student number, try to answer it. If it is a question, for example, about accurate and precise, you answer only 1 out of 4, yeah, for your student number, whichever is your student number, you answer only 1 out of 4, yeah. And if there is a code, usually it uses your student number, but not always. Sometimes the code does not use your student number, yeah. Okay, regarding the green sun, yeah, many other stars are also green, depending on the temperature of the stars, yeah. Okay. So do you have any specific questions? Because we don't really have much time to go through all the task, but maybe you have like specific questions about the task so that I will try to answer. Yeah. Okay, I'm going through the task then. So I cannot pull myself out of the mud because the internal forces cannot change the location of the center of mass of mechanical system. So the derivative of the kinetic energy with respect to velocity will be momentum, right? Because derivative of v squared will be 2v, and 2v divided by 2 will be just v, and m times v is momentum. And it is so important in physics because it is used also in quantum physics, in classical mechanics, in analytical mechanics. So this is potential energy, the laws of Newton. The mass can be inertial mass, meaning resistance to changing momentum, and can be gravitational mass, the strength of the gravitational force. Yeah. The weight is basically the gravitational force. My weight is approximately 750 newtons because my mass is approximately 75 kilograms. So on Earth, my weight is approximately 750 newtons. But on the moon, it will be six times smaller. Now, projectile, many questions in projectile. If you can find a test for the projectile, please do the test. For example, one of the tests can be if you can shoot at 45 degrees angle of release, and then you can compare it with minimum velocity, they should match. The minimum velocity and velocity at the angle of 45 degrees should match. That's one of the tests, okay? And there are so many problems about projectile. It is so important today when we are fighting in the wars. We really need to know a lot about projectile these days, yeah? So there are many questions about projectile, and they are all solved, or almost all of them are solved. Yeah, I give you the code for almost all of them, yeah? And I give you the equations. Okay, can you have no questions, no comments? Okay, I'm still thinking how to answer your questions and comments better. Okay, so many problems about projectile, how to hit the target as quickly as possible. And then also a question about track and trolley. Of course, track is more efficient because it applies torque to the wheels, whereas trolley pushes wheels or pulls wheels. Out of colliding eggs, the one which hits is more likely to be broken. And big foot is worse than small foot for the soccer player. We have discussed that before. Yeah. So for the air purifier, you just divide one volume by the other volume. Should be easy. The pulley problem, for the pulley, as you can see, I use the code N for the student number. And make sure my masses are correct. Masses must be L and T, okay? L and T, not TK over N and 2K, not 1 over K and 2K, no. L and T, yeah? And everything else is correct. So friction, you calculate the friction force. Dust particle using mv is equal to ft. Then the biker using mv is equal to ft. Solution, rotation. We can calculate acceleration due to rotation, centripetal acceleration or centrifugal acceleration, right? So we find, okay, breaking rope. Of course, it will follow the path of the mass, tangent to the circumference. Yeah. So we compare translation and rotation, and we can compare like solid mechanics and thermodynamics and electromagnetism there, or fluid dynamics. By the way, you probably are aware of the global warming. How much will the ocean level increase if all the floating icebergs melt completely? What do you think? Maybe it's hard for you to calculate, but you can give a guess. Like, for example, maybe 1 meter or 1 centimeter, or maybe 0, or what is it? What is it going to be if all floating icebergs melt? How much will the sea level increase? What do you think? Can you make a guess? Hello? Okay. 1 kilometer. Wow. 1 kilometer. That will be huge. No, of course not 1 kilometer. The truth is that it will be 0. There will be no change. Because from what we have learned from fluid mechanics and from thermodynamics, if the iceberg is floating and it melts completely, then the level of water will be exactly the same, yeah. But of course, the sea level will increase if the ice from the land will be moved into the water. That's for sure, will increase the sea level. And it does increase, but not 1 kilometer, maybe like few centimeters, like maybe 1 millimeter per year or something like that. It's not that quick. Yeah. Okay. If no other comments, let's continue. So translation and rotation are very similar, just like electromagnetism and solid mechanics are also similar in many ways, at least mathematically. Yeah. So then work, conservative laws, conservation laws happen when the force is potential, gravity force. So there is a difference in weight on the equator and on the pole because of the differences in distances, right? And I ask you to calculate that. Escape velocity and orbital velocity, and the gravitational acceleration g, lowercase. We can calculate it using what we know. Work energy theorem can solve almost everything in classical physics. Okay. For solid mechanics, we have torque, moment of force. Free body diagram is when you remove all the bodies and substitute them with forces. The body becomes free. Inclined plane with no friction, with friction, static friction, kinetic friction. Okay, there are so many solutions. Center of gravity can be a little bit different from the center of masses, sometimes significantly different. And the block stacking problem uses a center of gravity. Yeah. Well, for block stacking problem, the center of gravity will be the same as the center of mass. Yeah, it doesn't really matter in this case, but sometimes it matters. So we calculate angular acceleration, torque, and force. Okay. So again, rotational motion, rotational motion, rotational motion. Calculating potential energy and kinetic energy. So pulley problem for static equilibrium. So the masses are the same, and the tension in the cord will be mg, and it doesn't matter which m, because both masses are the same, right? So for the black hole, if we can compress something to small enough distance according to Newton's law of gravity, we can make a black hole out of anything which has mass. So there's the proof for the black hole. And this is the correction to Newton's equations if we move with very high speeds close to the speed of light. Yeah. So apparently there is chaos in classical mechanics. For example, double pendulum is chaotic. Okay, so inertia and inertial force is the result of reference frame not being inertial. Yeah, so I ask you to explain inertial force. Maybe inertial force is the result of attraction by distant stars. Maybe it's just a fictitious force. For solid mechanics, we calculate moment of inertia, and then we can calculate torque if we know angular acceleration, and if we know torque and moments of inertia, we can solve simultaneous equations and find acceleration, right? So this is the code. Okay. Okay, oscillation, pendulum and harmonic oscillator on the spring. So this is for the spring, period for the spring, period for the pendulum. Okay. And just like for the LC circuit. So the equations are almost the same, yeah? So displacement of harmonic oscillator, basically the solution is given to you. So this is the equation of harmonic oscillator differential equation, just like for the LC circuit, exactly the same, yeah? So you can solve it. Wolfram is really good for solving any kind of equation, any kind of mathematical problem. And the next one is forced oscillation without damping, so the resonance is possible. Okay, and this one is oscillation with damping, forced vibration with damping, similar to what we have considered for the electromagnetic oscillation. Yeah. So the waves, as you can see, the wave is exactly the same, almost exactly the same for the string, a guitar string. Yeah. And interference, I made a mistake here, but anyway, I forgot one of the brackets, yeah? But I think you can easily fix that one. Okay, any questions, any comments? No? The interference. Okay, here it's correct. So sound, just like the light, Doppler effect for the sound and for the light is basically the same, almost the same. Yeah. Elasticity and the force is conservative, so the derivative of the energy is equal to the force. Yeah. So the most general case for elasticity through tensor of stresses and tensor of this deformation and the tensor of elastic constants. Plasticity is a reversible change. Okay, if the masses are the same, then the tension which breaks pulley is going to be equal to mass divided by g, where g is the gravity acceleration. Yeah. So friction, elasticity, plasticity, and fracture, and also thermodynamics, and liquid and fluid, and they all have a foundation of electromagnetism as the force which is behind all those interactions, yeah? So we calculate the pressure of the fluid and we prove this equation. Buoyant's force, remember the problem of the icebergs that we discussed. Okay, Bernoulli's principle, the greater the pressure, the smaller the velocity, the greater the velocity, the smaller the pressure. Basically, this is the conservation law. Magnus effect is the curving of the balls, for example. In thermodynamics, also similarities with other chapters of physics. So the thermal extension. Okay, please ask me questions, please give comments, because I'm trying to help you to answer the questions. For example, in this case, for the expansion, as you can see, if your length is 1, if it is 1 meter, then it's much easier. Then the volume will change only 3 times greater. But if your length is different from 1, then you must do the cube of the expression, and you must subtract the final volume from the original volume. Yeah. So the long equation for V is for the case if L is not 1 but something else. But if L is 1, then the small equation will be enough. Yeah. Okay. So the thermal balance equation. Okay, then ideal gas equation, then real gas equation, and then what we discussed today, and the equation for the heat transfer, and then what we discussed today in electromagnetism. Okay, so I hope you can enjoy answering the questions. If you don't like answering some questions, just don't answer them. If you think it's too hard or too boring or whatever, just don't answer. But I hope that you can find something interesting, especially in your project. For example, some people try to use these equations to solve like practical problems of cryptography, of like pollution, predicting pollution, those kinds of things. And people are paid significant money for that. So maybe you can think of doing something like that. So from early stages of your studies, you can start doing your bachelor's project, because it's really hard to do the bachelor's project, because usually it's a very big work and usually you don't have enough time to do that. Okay. So then electromagnetism, the ones we discussed today, yeah? So any questions, any comments, please? Anything? Okay. So I wish you luck with the task. So you can always ask me questions. I will always try to answer them the best I can. And I think the deadline is 19th of October, which is in how many days from now? Is in 8 days from now. Yeah. So I will try to make your midterm exam very similar to the task 1. Maybe there will be task 2. We'll see. Maybe there will be no task 2. And if there will be task 2, then task 1 and task 2 will be just your, hopefully, your midterm exam. So if you can do task 1, then probably it's almost all your midterm exam. Yeah. So that's what I'm trying to do. I try to make tasks the same as the exams. Yeah. Anyway, so let's consider the star, because I think we need to do the star a little bit better. Yeah. Where is the star? There's astronomer observes Young's mirror. Oh, where is the star question? Oh yeah, maybe this one. No, not this one. Okay, maybe I can search. Anyway, I think we answered all the questions clearly enough so that you can easily answer them. Yeah. If you want something else, please do something else. There are books, there are publications on the internet. There are so good professors. There are such good professors on the internet. If you can search all these topics, you will find the best professors. They're young, they are from the best universities, and they explain so well. If you have time to watch it on YouTube, I'm sure you will understand most of it. And if there is something you don't understand, still you can ask me. I will try to help. Yeah. So what is the most difficult question so that I will try to help you to answer it? Okay. Okay. Any questions, any comments, please? Okay, look, if there are no questions and no comments, maybe we can finish for today. What do you think? Would that be okay? Hello?
Yes, sir.
So yeah, okay, yeah. Okay, then thank you so much for your patience, for your time and effort. You must be so tired. And I wish you luck. I'm trying to be useful. I'm trying to be helpful. And I will always try to do the best. So if you have any questions or comments or anything, please let me know. I will do my best to help, okay? So thank you so much. Terima kasih banyak. Okay? Thank you. See you soon. By the way, I will be in Trilogy University on Monday. Probably I will be there from 7 a.m. to about 5 p.m. So if you have time and if you have questions, if you have comments or anything, maybe you will meet me on Monday if you want. Yeah. Where we can collect. Yeah. So look, what I ask you to do, just answer in this task. I send you the file, the Word document, right? Just type your answers and change the code in this file and save it as your answers, and email it to me. Attach it to your email and email it to me, and I will check your answers. Just email me the answers, preferably. Just type your answers in the same file, save it as file of your answers, and email it to me. Okay? Okay. Any other questions? Any other comments? Okay. If no questions, no comments, then thank you so much. Terima kasih banyak. Thank you for your time and effort and patience. Thank you. Take care. Bye-bye.
Thank you, sir.
Bye.
Thank you, miss. Thank you, sir. Bye-bye.
Thank you, sir.